Okay, so today I want to drive you through a new course, which is quantum Shannon theory, where we'll talk about entropy, entanglement, communication. More especially, we'll focus first on compression. After we'll focus on channel coding. After we'll focus on LOCC and entanglement distillation. Um, After we'll focus on quantum stain, and we'll focus we'll do this basically. So quantum stain will do a part of the course, um, LCC and on distillation too, and channel coding too, and compression. And those two are less or more related, and this is the part itself on this too. So yeah, that's about it. And so today, to let you go through this course of quantum Shannon theory, which is like all of this, we'll begin so by compression, and on this compression, I would like to give you a little introduction of what we will be doing about compression with an example about quantum source compression. So basically, what you can think about is we'll try to find and discover an operation meaning of what it means. This quantum source compression, which can be represented after by the volume and entropy. But yeah, what's the operational meanings about it? So basically, we can first think about a source. So it can be a photon source, for example. Pew, it emits photon with states. It will create a states with a probability px, and you can think of this classically as if it was a bit flip. Like you have a coin and you have a chance over two that it goes on head, other one over two to go on tail. So mathematically, just it should be like your state could be represented by 0.5, like 1 over 2 of 0, 0 plus 1 over 2 of 1, 1. It's just like this. We just have one quantum state. It's into our hand, and so yeah, you can represent it that your friend told you, okay, bro, head or tail, which one will you choose? And so to represent it more formally and mathematically, you can write it as because it's not head or tail, you can have the sum of xpx of cx because we need this formalism about cx for two things, because first it's a statistical mixture, if the source has a 50% to cut the qubit into the 0 states, or 50% to cut the qubit in the 1 state, we cannot additionate together, because this is just giving in quantum one only state. It's not like head or tail, it's not like a classical, as I tried to explain to you, that's the classical stuff, and so you can represent it like this, but mathematically it does not work, because in quantum this state really exists as itself. In classical, you have some random stuff, is it head or tail, but in quantum it can be head and tail at the same time. So because of it, you do not want to just additionate it, because head and tail at the same time is already Soxim that exists. It's just like this. It's not head or tail, but it's between both. And so yeah, and you can represent it mathematically, and so yeah, it's not like classically, and so you don't have a random stuff like in classical. So you really want to have a matrix to represent it. And so the density matrix, which we wrote like this, get and bra, like it just the column vector with the line vector, multiply each together, give a matrix, and can represent this random stuff. Um, yeah, uh, yeah. Yeah, well, here we don't have the square root of 2 because that's the normalization into the quantum world, but yeah. So that's the first reason, like, because um, it will represent a quantum superposition as a Schrodinger cat that is died and alive at the same time, or the coin that turns two sides at the same time. But yeah, here it's a really random classical hazard, you know. So you want the density matrix to be able to make the distinctions thanks to this notation cx to present like it's like head or tail and not like living and died on the same time. And so yeah, so that's how you represent it quantitatively. And the second reason, so statistical mixture. So that's why we write it like this instead of just this. And the second reason is just because you want after when you use observable, like you do the trace of row AB of W with W being an observable, you want them the density your observable is like matrix, an observable matrix, and you need to multiply by an observable matrix. So when you have only this, it's not a matrix directly. So you want to write the matrix to have a multiplication of matrix, and after you trace the trace, so you have a number. But yeah, you need the multiplication between matrix because yeah, that's how it works to make multiplication of matrix and calculate trace. We need like row to be a matrix. So yeah, to a must for entanglement witnessing, for example, like you need to have like this observable stuff in mind, and so yeah, it's just a must for globally. It's a must for observable like matrix multiplication. Yeah, you got me, I think. So that's the first case where you have like head or tail if you want to represent, with your friend. And so after we can like try to do it into uh, your friend like give you the same stuff, but instead of doing like head or tail one time, he does it 1,000 times, but lets it 3 times. So suppose so you have your source again. Once again, probability px. You can differentiate by px1 if you want, and so you get px, and so you do it. I don't know, like n time, but let's say like, for example, it's like 3 times, and so your friend like give you 3 times the choice, and so every time like in the first choice, like if it's like 0, when you measure, he will put um, 0, in the first. He have 0 at first, maybe 0 after, and after 1, but every time like it's 1/2, 1/2, 1/2. So it means like if you multiply all of them, you have like n/8 for 3 cases. If n equals 3, you have n/8 chance to be correct on all on the 3 stuff, because there's 8 combinations. Yeah, so there's 8 combination. So yeah, it's like 12 over 5 for some chains. So yeah, because it's like 0.7 thing, and so 0 is like, yeah, just like 12.5. So you have this, and yeah, you just have the fact that when you check classically, you just see when you do this a lot of time, like you try at the first time 0 1 0 1, but not 3 times, but 1,000 times. You just check that at the end, like you still have like one over chance over two to have 0 and one chance over two of having one. That's basically the same principle into this quantum source compression. Um, but yeah, if we want to represent it, it's just like you have this multiple times. So you have, if you call your state for a to the power of n, it is the sum of x1. So it's literally the same as before, So instead of having x, you just have x1 to xn, and px1 to pxn, and cx1 to pxn. And yeah, you just do the same. So it's just like, and so instead of this, you just have positive px1 to pxn of cx1 to cxn. And so yeah, and so that's why I was explaining with something as density matrix, because of what I explained before. Uh, as I said, like mathematically, with the tensor product, um, you can just like to regroup all the different block, uh, um, and separate them from each one of each other. So just like this. So you do it for all of them. So it's just like sum of xn of pxn of cxn. Property being just basically just the linearity of the tensorial products, because like tensor product just behave like multiplication, like you can insert directly like probability inside the tensorial products. So yeah, you can associate the first peaks to the first box, the last peaks to the peaks, and to the last peaks and pxn because of the linearity. And in reality, there is two steps, like you first like separate them. Like first you have in a way the sum of x1 to xn, and you apply linearity of the half. You can have like px1 of px1 pxn, and after pxn pxn. But after, because you see x1 just depend on x1, x2 only on x2, etc., you can just separate and do the difference on their side by distributivity. So yeah, first linearity, and after we do like linearity, and after distributivity, I think it's called, and because it does not depend on the term itself, distinguish this different block that allows us to transform like this immense sum magically into a combination of those little density metrics isolated um, each by one another. So you see, we retrieve finally what we had at the beginning for one source, but multiple time. And so Because of this, we can just write that it is rho A XOR n, and so each isolated stuff like is identical to the density matrix of one source to solve the first example, and so we have these results like rho an which equal like XOR an, which is magnifical because concretely it signifies that for n quantum particles that are all independent one of each other, we cannot have to take a global giant sum. We can just take the one density matrix of only one particle and to multiply her by itself n times with the tensorial product, and that's what will allow us to apply the compression theorem, and yeah, that's literally the equivalent of the quantum format of a zip or point zip, or yeah, of our computers, like how to compress the maximum of quantum signal without like losing the substance. And von Neumann tree give us this, and you can just take like and it's easy mathematically to do it, like more easy that we called sort south at the first. So yeah, the goal is just like the comparisons, like to try to stock or transmit data of the source by using the less qubits possible without destroying information, like trying to have it intact. Great example of the goal of this is like just to try to go to put to the trash what is not useful and just consider what is essential, what is useful. So suppose you have like n qubits, you try to go into the typical subspace where we can compress. So typically like if having like A, B, 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 we can like say, well, it's just 5A, 5B. And so you just need 3 lambdas instead of, well, you just need 4 liters instead of writing it 10 times. It's more, it's easier to, yeah, so you compressed it in a way. So yeah, I think that's it for this quantum source compression introduction. Intuition, yeah.